This is section 1.1. We're going to talk about the 4 ways to represent a function. By the end of this video, you should be able to describe multiple representations of functions and evaluate and interpret function values. A function arises whenever one quantity depends on another. Consider the following 4 situations. The area of a circle depends on the radius r of that circle. The rule that connects r and a is given by the equation a equals pi r squared. With each positive number r, there is an associated one value of a, and we say that a is a function of r. The human population of the world P depends on time t. The table given estimates the population of the world P of t at time t for certain years. For instance, if I look at the table and I want to evaluate P of 1950, I can see that from the table it's about 2,560,000,000. But for each value of the time t, there is a corresponding value of p, and we say that p is a function of t. So even though this is an estimate and there's no explicit rule giving the relationship, I can still say that it is a function. The cost C of mailing a large envelope depends on the weight W of that envelope. Although there is no simple formula that connects W and C, the post office does have a rule for determining the cost C when the weight is known. And then the vertical acceleration A of the ground is measured by a seismograph, which is an instrument used for measuring the amplitude of earthquakes during an earthquake, is a function of the elapsed time t. And I've given you a graph sort of representing what that would look like. All 4 of these situations represent functional relationships. Essentially, a function is a rule, and it takes every element in a set D, and we'll call each one of those elements x, and it maps it exactly to one element called f of x in a set E. We usually consider the functions for which these sets D and E, those are sets of real numbers, and the set D is generally considered the domain of the function. The number f of x is the value of f, or the function, at x, and is read f of x. The range of f is the set of all possible values of f of x as x varies through the domain. A symbol that represents an arbitrary number in the domain is the function f is called the independent variable. When we're talking about a symbol, we're really just talking about a variable, any variable. We're talking about a variable. A symbol that represents a number in the range of f is called the dependent variable. So for example, in the first situation I gave you, r is the independent variable and a is the dependent variable, where r represents the radius of the circle and a represents the area. So as you change the radius of the circle, what will be affected is in actuality the area of the circle. The area will get bigger or smaller depending on how you affect the radius. It might be helpful for you to sometimes think of the function as a machine, and you've probably seen this diagram before of the function machine, where you pass in an input, and that input will be your independent variable x. Something happens in the machine on the inside, and that's going to generally be your rule, whatever you're doing to alter the independent variable, and then what comes out is the output, or f of x. If x is in the domain of the function, then x enters the machine and it's accepted as an input, and the machine produces an output f of x according to the rule of the function. So we can think of the domain as the set of all possible inputs, and the range is the set of all possible outputs of a function. Another way to picture the function is by an arrow diagram. Now this is probably getting a little bit more advanced. In the left sort of group of information, I have x, I have a, and I also just have a random point, which is a random data point. And I know that D is going to represent the domain of the function. And then E is going to represent the range, or f of x, of that function. And so I know that x is going to map onto f of x, a is going to map onto f of a, and the pink arrows generally represent the function rule. Whatever's being done to this independent variable to turn it into the dependent variable. Each arrow connects the element of D to an element in E. The arrow indicates that f of x is associated with x, f of a is associated with a, and so on. So I could put in as many points as I want. I could put in a B, and that would map onto a point in E, and that would be f of b, as long as B was located within the domain. The most common way in which we visualize the function, though, is with its graph. And so if f is a function with domain D, then its graph is the set of all ordered pairs. And so an ordered pair would just be x comma f of x. And this is just a fancy way of denoting that ordered pair. So it would be x comma f of x. And if you remember from sets, the bar actually means such that x is an element of this set D. But it's just boiling down to that you take x, you plug it into the function f of x, and you generate an ordered pair or a set of coordinates that you can plot, and that will actually trace out the curve of the function. And you usually see it as points x, y, and in our case we actually substitute y, which equals f of x. So the graph of the function gives us a useful picture of the behavior or the life history of a function. Since the y-coordinate of any point xy on the graph is y equals f of x, we can read the value of f of x from the graph as being the height of the graph from the point x. So if you look at the graph, this is pretty intuitive, but if I say that this is my x equals 1, then the distance from the x-axis to the curve would actually be f of 1. And then if this is x equals 2 in my domain, then the height from x equals 2 to the curve would be f of 2. And then suppose I replace that with anything, so I could say that if this is point x on the x-axis, then the height from this arbitrary x value to the curve is going to be my f of x value. So let's use this relationship, and oh, we're not there yet. Sorry, I got a little ahead of myself. What I can also use is the graph of this function, or any function, to describe the domain and the range. Essentially what we're looking for is the domain is going to be the interval of every single x value for which the function is defined. So in this particular y equals f of x curve, there is a distinct endpoint here and here. And so I can identify my domain as everything that happens in between these two endpoints. And similarly with the range, except the range deals with the lowest possible y value to the highest possible y value. And when you're looking at the graph, it'll probably be very easy to see maximum y values and minimum y values. Let's try one with it. So the graph of the function f is shown in figure 6. So let's find the values of f of 1 and f of 5. So if I look and I want to evaluate f of 1, well, I know that if this is x equals 1, and I know that the height of x is going to be, or the distance between the x-axis and the curve is going to represent my f of 1. So I know that this is going to be f of 1. Well, that's something that's very nice and finite and countable. So I can actually say that f of 1 is going to be equal to 1, 2, 3. I can just count it. But suppose I get to something that's a little bit hairier. Like if I say, well, what's the value of f of 5? Well, I know that this is 1, 2, 3, 4, 5. And if I look, I don't have a nice intersection here. So what I do know is that the distance from here to here is going to be f of 5. And if I wanted to, I could probably estimate it. It probably makes the most sense to estimate this value. We can use what we know about just number lines in general, but I can just estimate that, well, it's not even going to be an exact equals. It's going to be approximately, and since it's negative, it'll be a negative distance, and I'm going to estimate it at about negative 0.7. Now, this is not exact. Sometimes when we're looking at graphs, you don't have to be super exact, but we can definitely make a reasonable estimate that this is more than halfway, less than 3, and around 3/4. So I would say about negative 0.7. You could probably go as far as say negative 0.75 if you wanted to be really, really specific. Let's try the next part. If I want to find the domain and the range of this function, so to figure out the domain, and we know that the domain is going to be the set D. I look for the smallest possible x value, which in our case is going to be 0. So I know that my domain is going to go from 0 all the way up to 1, 2, 3, 4, 5, 6, 7. And it looks like it does include this point. As a side note, if it did not include that last point, you wouldn't see it solid. You would actually see a little circle on the end. But since we don't see that, we can assume that that last point is included. So I know that my domain is going to be the set x such that 0 is less than or equal to x, which is less than or equal to 7. And then the last thing I have to do is, if I'm going to state a domain in this set builder notation, is I have to assign x to a number set. And so I'm going to say that x is going to be an element of the real number system. Let's talk about the range. And we've been using the set E for the range, so we'll continue using the set E for the range. But in order to do this, I need to find the highest possible y value, which is going to be right up here at 1, 2, 3, 4. And the lowest possible y value, which is going to be at -2. Okay? And so what I can say is that the range is going to be the set of all outputs f of x such that, and we go in numerical order, so -2 is less than f of x, which is less than or equal to 4. And again, we have to assign it a value, so I'm going to say that f of x is in the reals. So if you remember from the first 4 situations, we have 4 different ways that we're going to be able to represent a function this year. The first is verbally, which you saw pretty much in all 4 situations. Each one was described by words. Numerically, which is a table of values, we gave that to you when we were discussing population growth. Visually, or by a graph, was with the seismograph, and algebraically was an explicit formula, or the area of a circle. So if you wanted to match it up with the situations that you had before, this was definitely situation C. Numerically was situation B. Visually was situation D. And algebraically was situation A. So let's take a look at a verbal representation of a function and see if we can take that verbal representation and translate it into something visual or graphical. So when you turn on hot water, or a hot water faucet, the temperature T of the water, it depends on how long the water has been running. Draw a rough graph of T as a function of time that has elapsed since the faucet is turned on. So if I know that the temperature T is dependent on time, generally the dependent variable will be vertical and the independent variable will be horizontal. And what I do know about, let's just use what we know about a hot water faucet. So when you turn the hot water on, initially the water's not hot. So it has to come from the hot water tank. So I know that if this is going to be a continuum of temperatures, I know that the hot water is going to start somewhere around room temperature. And as the water runs, the water is going to increase until it hits a maximum temperature of your hot water tank. And then that water is going to continue to run at that temperature as long as you have the hot water on. Now, in a perfect world, you would have an unlimited amount of hot water. But we know that this is actually not true. So when you think about when you run the hot water for too long, what's going to eventually happen is that you're going to run out and the tank's going to run out. And so you're going to start getting cold water back into your tap. And so after a period of time, your water temperature is actually going to go back down, and it's going to approach room temperature, and then once your hot water is completely out, it's going to continue going until you turn the sink off. So if we think the initial temperature of the water running water is close to room temperature because the water has been sitting in the pipes. When the water tank or water from the hot water tank starts to flow from the faucet, T increases quickly. in the next phase, so if we wanted to sort of annotate the graph, I know that this is the water heating up, and then all of this water here that's at a constant hot temperature, this is all coming out of the tank. And then from this point on, when the water starts to decrease in temperature, this is when we're running out of water. We're running out of hot water. And at this point where the temperature levels out, we're pretty much completely out of hot water. We're out of hot water. And so this is just an example of us taking a verbal representation of a function and translating it into a graph. Now, I personally think that the visual representation of this graph tells us a lot more about what's happening than just the two sentences that describe what the situation that we're given. Let's try another one. And this one's a little bit tougher. So a rectangular storage container with an open top has a volume of 10 cubic meters. The length is twice its width. Material for the base costs $10 per square meter. Material for the sides costs $4 or costs $6 per square meter. Express the cost of materials as a function of the width and the base. Now, if you think about it, we have a couple things happening here. One, I've already kind of filled it in. I know that the length is twice the width. So instead of having W, L, and H, I already know that if W is my width, then the length is going to be 2W because it's twice the width. And then the height of the box is just going to be H. I also know that it's $10 per square foot for the bottom. And I know that it's $6 per square foot for the sides. And then I also know, which is going to come into play later, that the volume is 10 cubic meters. So let's just figure out what it's going to cost to do the sides and the bottom, and then we'll deal with the volume aspect of it at the last bit, because that's what's going to give us the actual function. So first off, I know that it's $10 per square foot for the bottom, so I need to know the area of the bottom. So the area of the bottom, if I want to call it area of the bottom, it's going to be 2W times W, right, which is length times width, or it's going to be 2W squared. And I know that the area of the sides, well, I have two different sides. I have area of side 1 is going to be 2W times H. And I know that area of side 2 is going to be W times H, because we have two sets of different dimensions. So I have 2W times H for the front face, and then I have W times H for the side face. Now, what we do have to take into account here is that there is only one bottom, but there's two of each one of these. So I know that the cost, or I'll call it C for cost, is going to be $10 per square foot of the area of the bottom, so 10 times 2W squared, plus $6 per square foot of each one of the sides. So it's going to be 6 times, and there's also 2 of each one of these. So 2 times 2W times H, plus whatever this area works out to be, and there's going to be 2 of these. And that's going to be my cost function. So let's do a little bit of cleaning up of this function and see how far we get with it. So I know that C is my cost function, and it's going to be 20W squared plus, now if I multiply this all out, so it would be 6 times 2, times 2 times w times h. So this is 4 times 6, which is 24. So 24 wh plus another 12 wh. So you get c is equal to 20 w squared plus, this looks like 36 wh. Now, we're almost there, but the problem with this is that we want to express the function in terms of the width and the cost. So what I don't want is I don't want to have this h variable in my function. I don't want it, so I need to get rid of it. And the only way that I can get rid of it is using the last bit of information that I haven't talked about yet, which is the volume. So I know that the volume of this cylinder or this prism is going to be 2w times w times h. But I also know that the volume is 10 cubic meters, so I can actually replace this and say 10 is equal to 2w squared times h, and then I can solve for h. So h is going to equal 5 over w squared. And so I can take this value and I can plug it back in here, and I can finally get a cost function that is completely dependent on just the width of the box itself. And we've taken height out of it. So my cost function is going to be 20w squared plus 36w times 5 over w squared. And actually we can clean a little bit of this up too. This will cancel and that will cancel, and you'll get cost is equal to 20w squared plus 36 times 5, or 36 times 5 over w. And this is my function. Again, a very complex process to get to a very simple function, but it definitely tells us a lot more than just the words that are describing it. So let's take a slight turn. The graph of a function is a curve in the xy plane, but generally what happens, or the question that arises, is which curves in the xy plane of the graphs actually are graphs of functions. And the way that we do this is with the test that you guys already know about. It's called the vertical line test. A curve in the xy plane is the graph of a function of x if and only if no vertical line intersects the curve in more than one place. Basically what it means is that if you look at the two graphs below, the function or the graph on the left, this definitely is a function because you can draw a vertical line through any part of this graph and it will not intersect at 2 points. The second graph is not a function. Not a function. Because it fails the test. It fails right here, and here, and here. So you can draw a line through it and it hits through 2 points. So for example, if you think about the parabola x equals y squared minus 2, which is a little bit weird to think about, it's not a graph of a function of x because, as you can see, there are vertical lines that can intersect the parabola twice. So this fails the vertical line test anywhere along the domain of the function. The parabola, however, does contain the graphs of two separate functions of x. So if you notice, we can take x equals y squared minus 2, and we can do what we've always done to actually put it in a calculator, is that we can solve it for y. So by moving things around, you get y squared equals x plus 2. And so if you take the square root, you get y equals plus or minus the square root of x plus 2. Thus, the upper and lower halves of the parabola are graphs of a function, but the original function itself does not actually represent a graph, or represent a function. So if you look where the function or the graph on the left represents the square root of x squared, or x plus 2, and the graph on the right represents the negative square root of x plus 2. Each one of these individually represent a function, but together and written as x equals y squared minus 2, it does not represent a function. It fails the test. Let's talk about piecewise functions. So, if you recall, a piecewise function is defined by different formulas in different parts of their domains. A function f is defined by, so let's take a look at an example. If f of x represents the piecewise function 1 minus x if x is less than or equal to negative 1, and x squared if x is greater than negative 1. So what we're going to do is I'm going to have you evaluate each one of those 3 points and sketch the graph. If you want to look at evaluating some points, if I want to evaluate f of negative 2, I look at the value of x and I compare it to my inequality. Since it's negative 2, x is less than or equal to negative 1, so I'm going to follow the first rule. So it's 1 minus negative 2, which is going to be positive 3. If I evaluate f of negative 1, it'll be 1 minus negative 1, which is 2. And then if I evaluate f of 0, it actually fails this first test, so it actually has to jump to the next one, because 0 is greater than negative 1, so it'll be 0 squared, which is 0. To graph this, what I would recommend that you do is that you pick more values, say f of negative 3, f of negative 4, and then you go the other way, so you do f of 1, f of 2, f of 3, and you can start to trace them out. A lot of other functions can actually be used using, or defined using piecewise functions, and it actually makes them make a lot more sense. So, for example, if you think about the absolute value function, if I have the absolute value of a is greater than 0 for any value of a, in general, if we want to graph it, we say that the absolute value of a is equal to a if a is less than 0, or the absolute value of a is negative a if a is less than 0. This function can be written using a piecewise function, and it actually makes it make a lot more sense if you think about it. If my function is g of x equals the absolute value of x, and then this is the piecewise part of it, it's going to be equal to x for when x is greater than or equal to 0, and it's going to be equal to negative x when x is less than 0. So this is when it's equal to x for x greater than or equal to 0 for all x values, and this is where the slope is going to be negative x for x less than 0. Symmetry. If a function f satisfies f of negative x equals f of x for every number x in its domain, then f is an even function. For instance, the function f of x equals x squared is even because f of negative x is negative x squared, which equals x squared, which equals f of x. Basically what it means is that if you take, or if you want to see if a function is even, you take f of x and you substitute in negative x, and what you should get back is the original function. The geometric significance of an even function is that the graph is symmetric with respect to the y-axis, meaning that you can take a graph and you can fold it along the y-axis, and each half should lay right on top of each other. If f satisfies f of x is equal to negative f of x for every number x in its domain, then f of x is called an odd function. So, for example, f of x equals x cubed is an odd function because f of negative x equals negative x cubed, which is negative x cubed, which is negative f of x. Basically, if you take f of x and if you want to see if it's an odd function, you substitute in negative x to the function, and what you should get back is negative or f of x with a negative sign outside of it. Geometrically, what this looks like, this is called symmetry with respect to the origin, or rotational symmetry. Basically what it looks like is that it has been rotated 180 degrees, so if you take your graph and turn it completely upside down, you should get the same graph back. So let's determine whether each of the following functions is even, odd, or neither, because you can have the possibility that it is neither even nor odd. So if we look at the first function, f of x is equal to x to the fifth um, plus x, well, in both cases, what I'm going to do is substitute in f of negative x, which is going to give me negative x to the fifth plus negative x. And you should remember that any negative that's raised to an odd power is going to give me a negative back. So I know this is going to be negative x to the fifth minus x. And that's what f of negative x is. And then the way that I compare it is that, well, since I didn't get the same function back, I know that it's definitely not even. And so what I want to do now is I want to check to see if it's odd, so I will find negative f of x, which means I'll take a negative and I'll distribute it into x to the fifth plus x. And if I get the same function back as I did before when I evaluated, that means it will be odd. So when I distribute my negative in, I get negative x to the fifth minus x. And if I look, this is the same as this, which means f of x is an odd function. Let's try these two. The final thing we have to talk about is increasing and decreasing behavior. The graph in figure 22 rises from A to B and falls from B to C and then rises again from C to D. The function f is said to be increasing on the interval or the interval A to B, and decreasing on the interval from B to C, and increasing again on the interval from C to D. The way that we test to see whether or not the function is increasing is that we pick random x values in succession from left to right, and it is always from left to right, and we compare their f of x values. So I can say that, well, if this is my value f or x1 and this is my value x2, the height of f of x1 is less than the height of f of x2, and so the function is actually increasing. And so we can say that if we use our endpoints a and b, if I evaluate f of a and I evaluate f of b, then f of b definitely has to be bigger than f of a, and that would mean that the function is increasing. Similarly, from b to c, b is bigger than c, and so I can see that the graph itself is decreasing. It's actually very easy to see increasing and decreasing behavior from a graph. That's why graphically is probably one of the most common ways that you'll use to evaluate whether a function is increasing and decreasing, especially when we start talking about calculus and derivatives. But you can also do it algebraically. So notice that x1 and x2 are any two numbers between a and b, and x1 is less than x2. Then f of x1 is less than f of x2, and we use this as the defining property of an increasing function. So a function f is called increasing on the interval I if f of x1 is less than f of x2 whenever x1 is less than x2. So we generally keep it in order where x1 is less than x2, and then we evaluate which one is bigger. So if x1 is less than x2 and f of x1 is less than f of x2, then the function will be increasing. If x1 is less than x2 again, but the relationship on f of x is switched, so f of x1 is greater than f of x2, then the function will actually be decreasing. And that's something that happens from b to c here. So if I were to pick two more values, I call this, say, x3 and x4, and then I could match them up here, and this is f of x3, and this is f of x4, then I know that x3 is less than x4 on I, the interval, but f of x3 is greater than f of x4, so therefore the function is decreasing. from B to C. In the definition of an increasing function, it's important to realize that the inequality f of x1 is less than f of x2 must be satisfied for every pair of numbers x1 and x2 in the interval I with x1 less than x2. So you can see that in figure 23, if this is figure 23, that the function f of x is x squared is decreasing on the interval from negative infinity to 0, and then is increasing on the interval from 0 to infinity. So basically, this function, which is x squared, is going to be decreasing from negative infinity. And whenever we're talking about intervals, we're always talking about x values. So it's decreasing from negative infinity as we move to the right, and it's decreasing. And then as we keep moving to the right, from 0 to positive infinity, the graph itself is going to be increasing. That is the end of this video. We will be doing some applications in class with it. I know that it was a long video. I thank you for your patience. I'll see you in class tomorrow.